Let's get started on today's notes over radical expressions and rational exponents. And I first want to go over some vocabulary. This right here is read as the nth root of real number a. This n right here represents the index, plural, indices. The symbol is the radical, that's in green, and what's underneath the radical is called the radicand. So let's go over some types of radicals, the number of real roots that radical will have, and we'll look at some examples. So the first type of radical I want to go over is a radical that has an odd index. So that number right here, for example, is odd, and a positive radicand. So if that index is odd and what's underneath the radicand, is positive, you will have one real root. So the cube root of 27 is positive 3. And the reason that is because 3 times 3 times 3 is 27. So let's look at our next scenario. An even index, this right here is even, the fourth root, with a positive radicand. So what's underneath the radical is positive. If you have an even index and a positive radicand, you'll have two real roots. So the fourth root of 81 is actually positive and negative 3, because 3 times 3 times 3 times 3 is positive 81, but negative 3 times negative 3 times negative 3 times negative 3 is also 81. Now, anytime you're just given a problem like find the fourth root of 81, that indicates that you are looking for the principal root, which is the positive root. If you're solving an equation of some sort, that's when you'll have your positive or negative, if the case fits. So in the next scenario, we have an even index and a negative radicand. So in our example, the square root of negative 16, remember, if nothing is right here, it's assumed to be 2. So you actually won't have any real roots. So the square root of negative 16 does not have any real roots. So no real roots in this scenario. And then the very last one, if you have a radicand of 0, you'll have one root, and that'll be 0. So the 7th root, 8th root, 9th root of 0 is 0. So let's move on and find all real roots in these examples. So the cube root of negative 8 in example number 1. The cube root of negative 8, that's going to be negative 2. And why is that? Negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is 4. 4 times negative 2 is negative 8. So we've checked. The cube root of negative 8 is negative 2. Now let's look at the fifth root of 224 times x to the 5th, y to the 6th. So the first thing I want to look at is the numeric portion, so 224. And what I'm going to do is I'm going to find the prime factorization of 224. And I'm going to break it down like this. Obviously, it's even, so I know 2 goes into 224. 2 times 112. Also even, I know it's divisible by 2. 2 times 56. Also even, I know it's divisible by 2. 28. Oops, I'm sorry. Let me see if I can write that. 28, so 2 times 28. Also even, divisible by 2. 14, also even, divisible by 2. 7. Here's the prime factorization of 224. I've got 5 2's, so 2 to the 5th power times 7. Remember, if you're looking for the fifth root of something, I need 5 of a number to be able to pull 1 out. So 5 in the radicand to be able to pull 1 out. That's how you can kind of think of it. So because I have 5 2's, I can pull a 2 out. Now let's look at the variable portion. I have 5 x's, I have 6 y's. I need 5 of something to pull 1 out. So I can pull out an x, I can pull out a y. What am I left with as the radicand? I'm left with this 7 down here. And then I pulled all the x's out, and I pulled 5 of the y's out. I'm left with 1 y underneath my radical. And because we are looking at a fifth root, we need to make sure that we include this is the fifth root. So this would be my answer right here. So now let's move on to rational exponents. And this is kind of the bread and butter of today's topic, is being able to convert between radicals and expressions and rational exponents. So I can rewrite a radical expression using rational exponents. So that's just an exponent that's a fraction. The numerator of the fraction represents the power, and the denominator represents the root. And the denominator cannot be 0. So what I can do is I'm going to write this over here, power over root. So I can rewrite a to the power of m over n. I can rewrite it with that root right here as the denominator and the power right here. So that's n, the nth radical of a to the power of n, or the nth root of a to the power of m. But I also want you to note that you can write it like this. So you can find the nth root of a, and then you can raise that to the power of m, or you can write it like this, a to the power of m, and then find the nth root of that. So what we're going to do in this next little section is just rewrite expressions with rational exponents. So in 3 through 5, I'm going to take these expressions involving rational exponents, and we're going to rewrite them as radical expressions and simplify them if we can. So 4 to the power of 3 over 2. If I were to rewrite that, I'm looking for the second root of 4. That's just the square root of 4, which I know is a perfect square. And then we're going to cube that. And I'm writing it that way, okay, where I take the square root of 4 first, and then I raise it to the power of 3, because I know that 4 is a perfect square. What is the square root of 4? It's 2. So I'm actually going to take 2 and I'm going to cube it. And what is that? It's 8. So now let's look at example number 4. If I rewrite this power over root, I'm looking for the cube root of negative 64 to the first power, which I don't need to write that because it's assumed to be 1 if it doesn't have an exponent written. So the cube root of negative 64, again, I have an odd index, negative radicand, so my answer is going to be 1 real root, and it's going to be negative. That's negative 4, because negative 4 times negative 4 times negative 4 is negative 64. So let's look at example number 5. I've got 125 raised to the power of 2 over 3. So I'm looking for the cube root of 125, and I could square 125, but I also know that the cube root of 125 is 5. So what I'm going to do is I'm going to put that in parentheses and raise that to the power of 2. So the first thing I want to do is find the cube root of 125, which is 5, because 5 times 5 times 5 is 125. So that's 5 squared. And what is 5 squared? It's 25. So let's go on to our next section. And the next section involves rewriting radical expressions. So the first section, we're giving rational expressions or expressions involving rational exponents, and now we're given radical expressions, and we're asked to write each expression in, this should say, rational form. And I will change that on your notes. So we're going to write it as irrational. So remember, power over root, and if you want to rewrite that off to the side, power over root, absolutely, do that. Whatever little reminders you need to write on your sheet, always do that. So what I'm going to do is, remember, if you're asked to find the square root of 7, remember your index is assumed 2 if nothing is there. So if I were to rewrite the square root of 7 raised to the power of 4, that would be 7 to the power of 4 over 2, power over root. So can we simplify that rational exponent? We sure can, because 4 over 2 is 2. And then 7 squared, what is that? It's 49. So your best, the best advice I can give you when you get to this level of math is just simplify it as much as you can. And then if you can't anymore, leave your answer as is, as ugly as it is, because sometimes your answers are really ugly at this level of math. So when we get to number 6, power over root. So again, this could also be written like this, the 5th root of 2 raised to the power of 4. So you could see it both ways, but it represents the same amount. So if I were to rewrite this, it would be 2 to the power of power over root. 2 to the power of 4 over 5, and we can just leave our answers just like that. So in this next section, I want to go over your exponent rules very quickly. If you struggle with your exponent rules, I would encourage you to look at some previous videos over your exponent rules, and I'll put a little link in the upper right corner of this video that you could click on to get to a set of videos going over these rules. Okay, so because all of your exponent rules apply to rational exponents as well. So I'm going to go over these very quickly. The first one I want to look at is the product rule. And when you're multiplying 2 or more powers with the same base, you've got the same base, you can add the exponents. So if we look at our example, we've got 3 to the power of 3 over 2 times, again, I am multiplying, that's why it's called the product rule, times 3, again, same base, to the power of 1 over 2, I can add my exponents. You have to be really good at adding fractions here, because 3 over 2 plus 1 over 2 is 4 over 2. I can simplify that to be 3 squared, which again I can simplify to be 9. Let's look at our next rule, the power rule. The power rule states that when you've got a power raised to another power, so what you're looking for in this situation is if there's a set of parentheses and you have an exponent right outside the parentheses, okay, this n right here. That's kind of what when you're going to apply this rule. You can multiply your exponents. So in your example, we've got 4 raised to the power of 1/2, all raised to the power of 6. So what you can do is you can take that 1/2 and multiply it by 6. 1/2 times 6 is 6 over 2. I can simplify that fraction to be 3. 4 raised to the power of 3 is 64. Okay? So now let's move on to the next rule, the quotient rule. When you're dividing 2 or more powers with the same base, so again, here's your A, same base, what can you do? Subtract your exponents. So in your example, we've got 27 to the power of 2/3 divided by 27 to the power of 1/3. What can I do? I can subtract my exponents. So 2/3 minus 1/3 is 1/3. 27 to the power of 1/3, that's just the cube root of 27, which is 3. Let's move on to power of a product rule. So when a product is raised to a power, you can distribute the exponents. So I've got some multiplication going on inside of my parentheses, and I've got an exponent outside of the parentheses. So in our example right here, 4 times 25 raised to the power of 1/2, I can absolutely do 4 times 25 first, and then raise that to the power of 1/2, which is just finding the square root of 100. But what this rule tells you that you can do in different situations is I can take that 1/2 and I can distribute it to every term on the inside. So 4 to the power of 1/2 times 25 to the power of 1/2. Well, anything raised to the power of 1/2 is just, I'm taking the square root of that. These are two perfect squares here. So 4 to the power of 1/2, which is the square root of 4, is 2. 25 to the power of 1/2, which is the square root of 25, is 5. And 2 times 5 is 10. So now let's move on to our last rule that we're going to go over, and that's power of a quotient rule. So when you have some division going on inside of your parentheses, and again, you've got an exponent outside of your parentheses, you can distribute that exponent. So for example, I've got 8 over 27 to the power of 1/3. So instead of doing 8 divided by 27 and then finding the cube root of that, I've actually got a numerator and denominator that are both perfect cubes. So what I can do is distribute that to my numerator and to my denominator, 8 to the power of 1/3. Another piece of advice I can give you is to just interchange like the way you think between radicals and rational exponents. When I see anything raised to the power of 1/2, I know it's the same thing as finding the square root of it. And that's easier for like my brain to think about it. So anything raised to the power of 1/3, I'm taking the cube root of it. When you work with these numbers enough, you start memorizing your perfect squares and your perfect cubes. Okay, so I know that 8 and 27 are perfect cubes. The cube root of 8 is 2, and the cube root of 27 is 3. So 2/3 is your answer. And now we're going to move on to our next set of examples. So this says, to simplify each expression using the properties of radicals and rational exponents, assume all variables are positive. So we're just going to work our way through and think about them, using the rules that we've just gone over. And what I would encourage you to do at this level of math is whatever way you want to think about it, go with that way. And then if you feel like you're on the wrong path, start over, cross it out, move on, find another sheet, another sheet of paper, another place to show your work, and just start over and think about it a little differently, and you'll be fine. So right here, we've got 5 to the power of 2 over 3 times 5 to the power of 1 over 3. We're going to apply our product rule, and we're going to add our exponents because we've got the same base and we're multiplying. So that's going to be 5 to the power of 2/3 plus 1/3, which is, if I were to rewrite that as 5 to the power of 3/3, that's 5 to the power of 1, which is just 5. So let's move on to number 8, where we're going to apply our quotient rule. What do? We've got the same base, raised 2 exponents. We're going to subtract our exponent. So that's going to be 2 to the power of 4/3 minus 2/3, which is 2 to the power of 2/3. And we can leave it just like that. So that can be our answer. And if you think you want to write it as the cube root of 2 squared, or the cube root of 4, that's fine as well. Okay? So on number 9, I'm going to apply the power rule, where I have an exponent, a power raised to another power. I can multiply my exponents. So I've got 9 to the power of 3/4 times 2/3. And what do you get? You get 9 to the power of 6 over 12, which is 1 over 2. Again, 9 to the power of 1 over 2, we're taking the square root of 9. What is the square root of 9? It's 3. And that's your answer. Let's move on to number 10. And again, if, whenever I've just got these, you might be wondering, wait, if I'm taking the square root of 9, why wouldn't I say positive and negative 3? Well, again, if you're solving an equation, that would indicate that you will take the positive and negative square root of 9. But if I just have it right here, and I've just got it written out like that, where we're just simplifying it, we're going to take the positive root. Moving on to number 10, the cube root of negative 16 times the cube root of 4. So we're going to go back and apply our operations with radicals rules. What can you do if you have the same root? Well, I can multiply my radicands. So that would mean I have the cube root of negative 16 times 4, which is negative 64. And, I can't simplify each of these, right? I can't find the cube root of negative 16, and I can't find the cube root of 4. But guess what? I can find the cube root of negative 64. It's negative 4. Let's move on to number 11. So what I'm going to do here, you can kind of go about this using, I could find the cube root of 8 in my denominator first if I wanted to, right? Because it is a perfect cube. So that could be 2. What I'm going to do is I'm going to go ahead and rewrite this as the cube root of 192 divided by 8, right? Can I rewrite it like that? I sure can. So what is 192 divided by 8? It's 24. So now we're looking for the cube root of 24, and that's all I'm going to do is simplify the cube root of 24. So whenever I'm finding the cube root of 24, what I'm going to do is I'm going to find the prime factorization of 24. So 24, it's obviously divisible by 2 because it's even. 2 times 12, even again, divisible by 2. 2 times 6, divisible by 2. 2 times 3. So some of you might have done the tree or whatever, your factor tree. This is how I'm doing the prime factorization here. So again, if you have 3 of something, you can pull 1 out. So I can pull a 2 out, 2, times the cube root of what's left over, 3. So that's how I would simplify that. Let's move on to number 12. I've got the fifth root of 4 divided by the fifth root of 8. So I'm going to rewrite this as the fifth root of 4 over 8, which would simplify to the fifth root of 1 over 2. And that's actually how I would leave this, right? The fifth root of 1 over 2. If you wanted to rewrite it as 1/2 raised to the power of 1 over 5, you could. But that's how I'm going to leave my answer here. Moving on to number 13. Let's look at this example. Okay, I've got a power raised to another power. What do I do with my exponents? I multiply them. Okay, I'm going to rewrite this so you can really see this. Square root of 2 times 4 square roots of 2, or 4 root 2. What can I do when I'm multiplying radicals? I multiply the radicands. So that's going to be y raised to the power of 4 times the square root of 2 times 2, which is 4. 4 is a perfect square. What is the square root of 4? It's 2. So this would be y raised to the power of 4 times 2, which is y raised to the power of 8. Let's move on to number 14. I've got the cube root of x to the 5th times the cube root of x to the 4th. Okay, I've got the same index. So what can I do when I'm multiplying? I'm just going to add those exponents, right? I'm going to combine the radicands. So multiply x to the 5th times x to the 4th. Well, that's x to the 9th. So I'm going to rewrite this as the cube root of x to the 9th raised to the power of -2. So let's first tackle what's inside our parentheses, the cube root of x to the 9th. So I've got 3 groups of 3 x's underneath my radical. So those 3 groups, I can pull 3 x's out if that's how you think about it, right? So what this is, and I could simplify that as like the power of 9 over 3. Maybe I should write that down. So I could rewrite this as x to the power of 9 over 3 raised to the power of -2. 9 over 3 is 3. So this is x to the power of cubed to the -2nd power. So now what do we do? Well, I can distribute that -2. I can multiply it. That is x to the power of -6. And then how would I rewrite this? Using positive exponents. So negative exponents, that's a rule that we did not really go over. But x to the power of -6 implies a really, really small, or implies division, basically. So x to the power of -6 I can rewrite as taking the reciprocal 1 over x to the power of +6. And that's how I would write that answer. So let's move on to our last example. I know this is a really long set of notes. And I've got x cubed divided by 81 raised to the power of 1 over 4. So what I'm going to do first is I'm going to take that 1/4 and I'm going to distribute it to each, my numerator and denominator. So in my numerator, that would be x to the power of 3 over 4, which I could rewrite as the 4th root of x cubed, right? Couldn't I do that? Over the 4th root of 81. 81 to the power of 1 over 4 is just the 4th root of 81, which, what is the 4th root of 81? It's 3. So I can rewrite this as the 4th root of x cubed over 3. Could you write this as x to the power of 3 over 4 over 3? Sure, that also works. You know, it represents the same amount, and so typically when you're in upper level math, your teacher is typically okay with those types of things. So I know this was a long set of notes, but I hope it was helpful. Good luck.